She is my student. She will tell us about phaseless PCA, low rank matrix recovery from column-wise phaseless measurements. Looks like she changed the title from what she sent in the abstract, but that's okay. Sara has been a PhD student in the Department of Electrical and Computer Engineering at Iowa State for about 4 years now. Previously, she was working in the Signal Processing Research Lab at Sharif University, where she got her master's. Her research interests are in various aspects of information science and focus on computer vision, signal processing, and statistical machine learning. What else does she say in her bio? And yeah, after the talk, we'll have time for discussion. So, Sara, all yours.
Yeah, sure, thank you. So phase retrieval generally is a problem that wants to recover this and lens signal X star from its phaseless magnitude-only linear projections of its this signal. So we have measurements of the form of this form, which YIs are the measurements are known, and is the absolute value of the inner product between the design vectors AIs and the signal X star. So for I between 1 to m, we have design vectors and the signal X star. So the design vectors AIs and the measurements YIs are known, but we don't know anything about the signal X star itself or the phase of the measurements. So because this is absolute value, so we don't have the phase. So applications of this problem can be any application that recovering the phase is hard or difficult or impossible. So like Fourier imaging problems and, for example, Fourier tachography, which recovering the phase is difficult. So there are many, there are some provable solutions for this problem. Like the phase lift, non-convex solutions, alt-mean phase, Wirtinger flow, truncated Wirtinger flow, and reshaped Wirtinger flow. So the two of most recent and popular methods for this are the truncated Wirtinger flow and the later work reshaped Wirtinger flow, which they have the optimal sample complexity, and their sample complexity is in order of the signal X star, the length of the signal. And they also have the best time complexity. The time complexity of them is in order of n log of 1/epsilon. So as you see, without any structural assumptions, we need at least the sample complexity of in order of the length of the signal X star. So if we want to reduce the sample complexity, we need to assume some structure for the signal, for example, a sparsity or a low rank structure. A sparse phase retrieval is well studied and assumes X star is sparse. The other common structure is low rank, and which is what we also assume for the signal. So there are two ways to impose this structure. One is to assume the signal X star is being imaged and can be rearranged as a low rank matrix. This is not studied and is not a practical way approach for most settings because we don't have access to the pixels of the image. So this is not studied. And the other assumption which we use in our setting is to assume that we have a set of signals xk stars for k between 1 to q. So we have a q set of signals xk star, and we assume that they together make a low rank matrix. So they are the columns of a matrix which is low rank. And this is a more practical and commonly used model. So for example, it can be used in face recognition or recommender systems. And for phase retrieval, this can enable fast phaseless dynamic imaging, for example, Fourier tachographic imaging of live biological specimens. So in our setting, our problem is that we have a set of signals x1 star to xq star. So they together make the columns of a matrix x star here. So which this matrix is of size m by q and is of rank r, which r is much less than the dimensions of the matrix. So it is a low rank matrix. And we have measurements of phases measurements of the form we said of each of these columns. So we have m phaseless linear projections of this form for every column xk star. So the measurements and the design vectors AI cos for I between 1 to m, k between 1 to q are known. But we don't know anything about the phase of the measurements via cos and the xk stars. So even the linear and with phase version of this problem is not well studied, and so this problem is different from both low rank matrix sensing and low rank matrix completion. It is different from low rank matrix sensing because the low rank matrix sensing aims at recovering the matrix X star from measurements, the global measurements, and by global I mean the yi's here depend on the entire matrix X star with AI is dense. And it is different from low rank matrix completion. So low rank matrix completions recovers X star from a subset of its entries. And the measurements here are completely local and needs both rows and columns to be dense to allow for correct interpolation. So our problem is different because we have non-global measurements of X star, but global for each column. So because of that, we only need the denseness of rows or incurrence of right singular vectors. So for some notations, we have our guarantees assume that the design vectors AI cos are IID standard Gaussian real vectors, and we have the prime, the method notation for the transpose, and the phase invariant distance is defined here like this. So this between the distance between X star and X hat for two vectors is the mean of this quantity. And so this, for a real case, this simplifies to the minimum between the norm of X star minus X hat and norm of X star plus X hat. So, so because the matrix X star is low rank, it is possible to decompose it to two matrices, U star and B tilde star. So if we have, for example, if we consider the SVD singular value decomposition of the matrix X star, this is nothing but U star. So if the singular value decomposition of matrix X star is U star sigma star V star transpose, so we have X star is, we can write it as U star B tilde star, which B tilde star is sigma star V star transpose. So if we consider this decomposition of the low rank matrix X star, so each column can be written as xk star equal to U star bk star tilde. So we can rewrite xk stars as like so, and which U star is M by R matrix with orthonormal columns. So our problem is, if I want to restate it, so we have a set of signals x1 star to xk star, and we can write, we want to recover the each of the matrix, and so we have measurements via case for each of these each of the signals xk stars of this form, and so we can also write xk star as U star B tilde k star, and so it is possible, if you see that, we can also write the measurements via case like this. So it is the inner product between U star transpose AIK and BK tilde star. So then this is useful in our algorithm, because if we have at the first step a truncated spectral initialization or an initialization for U star, then for recovering BK stars, we because this is a Gaussian, and so for recovering, if we have the, assume we have the U star available, so then recovering each BK tilde star can be just solving a small or dimensional standard phase retrieval problem. So because the standard phase retrieval problem is needs sample complexity of the order of the length of the signal. So here BK tilde stars are dimensional, and it is an easy small standard phase retrieval problem. So after the initialization and recovering the BK star, so here, because I was saying we assume that U star is available. So if U star is not available, we can have a good estimate of BK star with a good estimate of U star. So with good estimate of BK tilde stars and U star, we can have a good estimate of xk star. So this also gives us a good estimate of the phase or sign of the inner product between AIK and xk star. So by using this phase and sign, recovering the subspace estimate is just a simple least square problem, and it can be solved like this. And then because this estimate is not necessarily orthonormal, so we can have a keyword decomposition to make sure that this is an orthonormal estimate. So this can be used as subspace. So the key insight to get a sample complexity gain over the standard phase retrieval here is that condition on X star, we have MQ mutually independent measurements, and they are not identically distributed, but we have a writing coherence assumption that enables us to assume that they are similar enough. So this is also useful for using the concentration bonds which are available. So the initialization of our algorithm is inspired by our previous work and the truncated Wittinger flow by Candace. So it's a modified version of both. So we have, for this, we consider a matrix YU pool, which is of this form. And it can be shown that it is not hard to see that the expected value of this matrix is equal to this. And so hence, if MQ is large enough, by law of large number, the span of top or left singular vectors of YU full is a good estimate of a span of U star with high probability. Here, these are heavy-tailed, and because these are heavy-tailed, so a few bad entries, large measurements can bias the average, and then if this happens, we need a larger value for MQ sample complexity to be to solve this. So to fix this problem and to don't deal with the heavy tail quantities, so we can use the truncated version of this, which here you can see the truncated version. And then we use a YU of this form, and the initialization estimate of subspace U can be top or left singular vectors of this quantity. So here, this allows that we throw away the bad wire cos here, and so it needs less sample, less value for MQ. So this is the algorithm we are using, Altman for low rank phase, Altman low rap. So first we have the initialization. We consider the top power has singular vectors of this matrix, which is that truncated version, and is using the full samples here. And then we have the iterations for the main loop. So first we recover each BKs with coefficient vectors with simple phase retrieval of this one for I between 1 to M, K between 1 to Q. After that, with initialization and or the previous estimate of the subspace and this recovered coefficients, so we can have the estimated version of the matrix X, and by having this, we can have also the good phase estimate, and by using this, recovering the subspace is just a simple least square problem. So we also have QR decompositions for both B and U. So for recovering the B case, we can use a standard phase retrieval problem, and this can be any phase retrieval that is available. So here, for example, we use RW, reshaped multi-shape flow. So this is our main result. So if you remember, we want to recover the matrix X star, which is a low rank matrix of size m by q, from the measurements of each of its columns. The columns are xk stars, and the measurements are of this form for the design vector between, so the design vectors AIKs and YIKs are known, and we don't know anything about xk stars or the phase of the measurements. So here I between 1 to m, k between 1 to q, we have measurements of each of the columns of x star, phaseless measurements. So having this with the algorithm we saw, if we assume mu occurrence of right singular vectors of x star with this much iterations, and also with assuming that we are using a new independent set of NQ measurements, we can recover with high probability every column with good with error epsilon with sample complexity MQ greater than order of NR4. So this means the total sample complexity will be in order of NR4 log of 1 over epsilon, because we have this much iteration. And so here C is depends on kappa and mu, which we here consider kappa and mu as constant. So the time complexity will be MQ and R log of to the power of 2 of 1 over epsilon. So as we can see here, the sample complexity is in order of NR4. So because the matrix X star is low rank, we can decompose it to two matrices, U star, B tilde star, which U star is of size M by R and B tilde star is of size R by Q. So the total number of unknowns here are n plus q times r, which is approximately 2nr. So we can see that here the sample complexity is in order of nr4, which is r cubed times the optimal value or the number of unknowns. And also, if one wants to recover each of the columns xk star with a standard phase retrieval, so a standard phase retrieval needs m sample complexity in order of n, or the length of the signals. And so for each column, we need n, and the total for the total k column, q columns, k between 1 to q, we need sample complexity at least in order of q, nq. So when r is much smaller than q, or 4 is smaller than q, then this is much better than the standard phase retrieval. So this is also, again, we have the optimal value, or the number of unknowns is in order of nr, 2nr. So the sample complexity here is r cubed times log over 1 epsilon of the optimal value. And in comparison with the standard phase retrieval, this is much better when r4 is much less than q. So there are also no existing guarantees for this problem. The closest low-rank recovery problem with non-global measurements is low-rank matrix completion. And also the sample complexity of non-convex low-rank matrix completion solutions is suboptimal. For example, after 10 years research, the best low-rank matrix completion solution with projected gradient descent needs sample complexity of order of NR2 log to the power of 2 of n samples. So an ultimate complete needs CNR 4.5 log of 1 over epsilon. So here, if, for example, R is in order of log over 1, log of n, then this is almost the same of our sample complexity. So the proof outline for our work is like so. So we have for spectral initialization, we can show that the distance of the initialized value for the subspace U naught is near is delta unit from the U star. So here this means the distance is subspace error between U star and the initial estimate of the subspace. So after that, as we talked, recovering of the subspace coefficients is a noisy phase retrieval problem, and this is the value of the noise. So we show that the distance between the estimate of coefficients and the rotated version of it, which is U transpose U star bk tilde star, is less than this value. So we are using here the rotated version because it is possible that we recover a rotated version of the coefficients, and we cannot use the distance, the usual norm distance between bk hat and bk tilde, because we can have rotation, and then this can be large. So after that, we use this to show that the similar bound is also correct for distance of x hat k, or the estimated version of xk, and the true version xk star. And also we use this to show that the estimated coefficients are also incurrent with mu hat equal to c kappa mu, and this is with this probability. After that, we show geometric improvement for recovery of U star. We show that as long as this value is less than C over R, the subspace error between U star and nu t is less than 0.7 to the power of t times delta unit. So this is with this probability because this is using the previous claim. And also, since xk star and xk hat are close, with that probability, the sign of aik xk star and aik xk hat are equal. So probability of unequal sign is large only when this value is comparable with the distance between xk hat and xk star. So since distance between xk hat and xk star is small with high probability, this doesn't happen very often. So this happens rarely. So for the initialization, for the proof of initialization, we first sandwich y(u) between y minus and y plus, which y plus and is this value with 1 plus epsilon 1, and y minus is the same with 1 minus epsilon 1 here. And then with sine theta theorem, we can show that distance between the subspaces U star and U, the initial value of subspace, is can be written like this. And then we just need to bond the numerator and denominator. So here we also bond this value, lower bound this value, and upper bound this. So, and then we conclude that the initial value is a good estimate with high probability. So for recovering the coefficients, BK tilde stars, we instead, because we can have rotation, we instead recover the GK, which is U transpose XK star. And this requires measurements of this form. So this can be solved with simple phase retrieval, Richet-Bertinger flow, for example. And by theorem 2 of this paper, we can show that when M is larger than or is in order of R, the dimension of BK tilde star, with this probability, we can show that distance between the rotated version of BK tilde star and the estimated coefficients is less than this value. And then also we need to bond the new case. And by having enough iterations of our W, we can have this so using this, we can also show that the distance between xk hat and xk star is small enough, is 1 plus c times delta t times the norm of xk star. So after this, recovering the U, by linear algebra, we can show that U is can be written like this. And so the distance between ut plus 1, which is the estimated U in iteration t plus 1, and U star is less than some quantity like this, which the main term here is max of term 1, term 2 over mean of term 3. So term 1 is like this, term 2 here and term 3 here. And here SW is the set W in of size n by R matrices W with norm frobenius equal to 1. So for this, we need to upper bound the term 1 and also term 2, and upper and lower bound term 3, because in term 2 we also have something like term 3. So these are some results. So here our algorithm is the green one for both pictures. So we can see that it is working better than reshape integer flow or our previous work, and also projected RWF, which is projected reshape integer flow, and it's the reshape integer flow projected onto the space of low rank matrices. And so here also we can see that our algorithm is working better. Here RWF and the TWF, truncated integer flow, and reshaped integer flow, which are two of the most popular recent works for standard phase retrieval, are using m equal to 4n. So our algorithm is using m equal to n over 4. So it is roughly 5 times faster than both of these algorithms. And so here n and q are 600 and 1000. So also this is a real video of a moving mouse. So these are the original frames of 3 frames of a moving video of mouse. So this is the recovered picture frames by our algorithm, and this is for reshaped integer flow, the results for reshaped integer flow, which is one of the existing optimal phase retrieval problem and recent works. So also, if you want to see some videos here, for example, this is the videos of the mouse. So this is the recovered video of our algorithm at the bottom. And also these are some other videos. And so if you have any questions, I will be happy to answer.
Okay, so are there any questions for Sara?
Sarah, this is Jonathan Smith. I did have one question. It wasn't quite clear at the beginning. You said you reject those outline Ys. I wasn't sure, is that automatically done in your algorithm?
No, actually it helps because
Sara, we can't hear you too well.
okay. So can you hear me?
Not very well. Are you facing the microphone?
Yeah, actually, so I didn't change anything. So
yeah, so my question was about this truncation.
okay.
I couldn't tell, was that done automatically in your algorithm?
Oh, yeah, yes, it is automatically.
Okay, and had you looked at the time complexity for that? Is that an issue or not too much?
Sorry, can you repeat?
Yes, that truncation.
Okay.
Did you factor in the time to do that, or is it just not an issue?
So Sarah, did you spend so the question is, does it take extra time to do the truncation?
Oh, no, actually. So it's not too time consuming.
Maybe you can explain what you mean by truncation.
Yeah, so actually we are using just those biocos which are near the mean. Here we are summing over those biocos which is less than the 9/MQ. This is the empirical mean times some constant. So because so because there are a few bad large measurements which can make the needing which then we have to use more MQ. So
okay, and for example, in your video cleanup,
So does that
would
answer your question, Jonathan?
Sorry?
Does that answer your question?
Yes, but I just had a follow on. I'm trying to understand these, what these Ys are in practice, these bad ones are in practice. So in the video example, can you say what that would correspond to? Would it be like some kind of interference on a video image, or what does that correspond to in practice?
Yeah, actually maybe
Sarah, speak up and speak into the microphone.
yeah, actually I'm trying.
Yeah, now it's good. Now we can hear you.
Okay. Yeah, actually, I'm not sure how to describe it for a video, but so actually here we have so if we don't use the truncation, so we have this heavy-tailed thing. So when we are using the truncation, this can be sub-exponential. The whole thing can be a sub-exponential thing, and so it needs less value for MQ.
So to follow up in responding, so Jonathan, the YIK, the measurements are linear projections of the videos. Okay.
Yeah.
Or magnitude only linear projections of the videos. Each YIK is, you take the kth video, take a random linear projection of it, or sorry, random linear projection of it with AIK, which is essentially a random Gaussian image, followed by taking only the magnitude. Okay, so we are when you say throwing away bad measurements, what you're really doing is you're throwing away those measurements in which case AIK happens to be too far away from the video, right? So the angle between AIK and the video is large, right? So AIK is a vector. Video arranged as a one-dimensional vector is my X star K. And if the angle between these two vectors is very small, then YIK will be small, magnitude, correct? And we don't want to use those in our average computation.
Okay, thanks. Yeah, that angle idea, that's very helpful.
Yeah, so that's the point. You want to use, because what you really want is you want to basically show that the expected value, so you want to use only those YIKs so that the expected value of YIK square is equal to the norm of the video squared, right? You'd like that.
Yeah.
And you can't do it exactly, but you'd like it to be close with high probability. So That's why you're doing this. And,
Okay, thank you.
and the original idea goes back to the site reference, the truncated vertical flow reference provided here on the slide.
Yeah.
Or I should say original in engineering. I'm sure it's been used earlier elsewhere. Okay, good. Other questions? Okay, I'll give it 2 more minutes and maybe we'll wait till 12:50, otherwise we can end sooner. Okay, so thanks everyone. I guess we can end today's session. Unless there's any comments, questions, suggestions, thoughts. All right, then see you all next week. Bye.